Have you ever wondered how calculus was discovered? It's an interesting story containing some of the greatest mathematicians of all time, and a little controversy too. The origins of calculus go way back more than 2,500 years to the ancient Greeks, where we begin our journey to the birth of calculus. In 400 BC, Greek mathematician Eudoxus used a method of exhaustion to find the areas and volumes of shapes. He discovered that the volume of a cone was 1/3 the volume of its corresponding cylinder. At around 240 BC, Archimedes developed this method of exhaustion further to prove that the area of a circle was equal to pi r squared. He did this by drawing regular polygons inside a circle until the regular polygon had so many sides it had practically become the circle itself. By coming up with the formula for the area of a circle, Archimedes invented a style of mathematics called heuristics. This was an approach to problem solving that's not quite perfect, but it's still practical and sufficient enough. Heuristics started to resemble early integral calculus, and Archimedes used the method of exhaustion to calculate further areas, such as the area under a parabola and the surface area and volume of a sphere. Archimedes was also the very first to find the tangent to a curve rather than just a circle, using a method that started to resemble differential calculus. When studying the spiral, known today as the Archimedes spiral, he separated the point's motion into two components, one radial and one circular motion. He added the two motions together, and by doing this was able to find the tangent to a curve. Moving on now from ancient mathematics and now fast forwarding to the 17th century. At this time, often called the century of the scientific revolution, many great mathematical ideas, formulas and proofs were discovered. Cavalieri developed a method of indivisibles in the 1630s, which was a more modern version of the method of exhaustion by Archimedes and an early step towards integral calculus. Cavalieri's principle states that if we have two solids of equal height sitting on the same plane with equal cross-sectional areas, as though we have sliced these solids up into flat cross-sections, then the volume of these two solids must be equal. Other European mathematicians in the 17th century, such as Isaac Barrow, René Descartes, Pierre de Fermat, Blaise Pascal and John Wallis all began to discuss the idea of something called the derivative. But the two most notable mathematicians of this time, Isaac Newton and Gottfried Leibniz, were about to make one of the most incredible breakthroughs in mathematics of all time. In the mid-1600s, at the peak of this scientific revolution, a young man called Isaac Newton was living in Cambridge, England. As a teenager, he was removed from school, and his mother, widowed twice, tried to make a farmer out of him, but Newton hated farming. The master of King's School eventually convinced Newton's mother to send him back to school so he could complete his education, and it's just as well that he did. He quickly became a top-ranking student and stood out from his peers by building things such as sundials and windmills. In 1661, he began his studies at Trinity College, Cambridge. However, in 1667, Trinity College was closed due to the precautions from the plague. During this time, the 22-year-old Newton was trying to solve physics problems, but he needed to come up with some kind of dynamic mathematical system to help explain his physics problems of gravitation, motion, and the orbits of the planets. Foremost, he was a physicist and he worked extensively on laws of motion and gravitation. But no mathematics yet existed to explain how an object falls, increasing in speed every split second. Newton also wanted to work out why the orbits of the planets were ellipses, and as a result he developed infinitesimal calculus, building on the work of European mathematicians such as René Descartes and Pierre de Fermat. By forcing a relationship between physical phenomena like the laws of motion, gravitation and the orbits of the planets, he saw the need for the development of a whole new dynamic system of mathematics. So how did he come up with this dynamic mathematical system? The initial problem confronted by Newton was that it's easy enough to find the average gradient on a function using rise over run, such as the average speed on a distance time graph. However, what happens when the slope of the curve is always changing? A method didn't yet exist to give the exact slope on any point on a curve that was changing its rate multiple times. Newton started to realise that as the secant of a curve becomes smaller and smaller, the slope becomes an exact point, and we can draw a tangent at this point. We know that the tangent is a straight line that only touches the curve at one point. And so, as the secant approaches 0 to become the point on the curve, the calculation of the slope becomes closer and closer to the exact slope at this point. This is when Newton calculated something called the derivative or gradient function, which can accurately give the slope at any point on any function. Newton called this process of calculating the instantaneous rate of change the fluxion, and the changing y and x values the fluence, which is the differential calculus we use today. Once he had come up with the derivative function, or the gradient function, Newton established that it's then really easy to find the instantaneous rate of change on any curve at any point by just inserting a value for x. Newton then came up with the discovery that the opposite of differentiation is integration, and he named integration as the method of fluence. In his fundamental theorem of calculus, where Newton links integral and differential calculus, he states that differential and integral calculus are opposites or inverse operations, so that when you differentiate a function and then integrate it, the original function is retrieved. So what exactly is integral calculus? The integral of a curve is the formula for calculating the area bound by the curve in the x-axis between two x points. The area under a velocity time graph, for example, would be the actual distance travelled. Integration can be achieved by breaking the area into infinitesimally thin rectangles and then adding up all the areas of all the rectangles to get the exact area under the curve. The thinner the rectangles are in their width, the more accurate the area under the curve would be, which eventually would approach the exact area. This is known as a limiting procedure, as the width of the rectangles approaches 0, in the same way that the length of the secant approach 0 for differentiation. The development of mathematics by the Greeks up until this time was very static. However, calculus would allow for mathematicians and engineers to really make sense of motion and dynamic change in the world around us, such as the orbits of the planets and the motion of fluids. Newton was considered one of the most influential figures in history to this day, and in 1687 he published Principia Mathematica, the principles of natural philosophy which dominated the scientific view of the universe for the following 3 centuries. Moving on now to the second discoverer of calculus, Gottfried Leibniz. Gottfried Leibniz, born in Germany in 1646, was son to a professor of moral philosophy. He was lucky enough to inherit his father's personal library, who unfortunately died when he was only 6 years old. His father's library enabled him to study a wide variety of advanced philosophical and theological works not available in general schoolwork. He was only 18 when he graduated with a Master's in Philosophy, and after only 1 year of legal studies, he was awarded a Bachelor of Law. After meeting mathematician and friend Christian Huygens, he convinced Leibniz to dedicate time to the study of mathematics. And so in 1674, Leibniz began working on calculus. His approach to calculus was from a metaphysical point of view. He reasoned that the integral was the sum of the ordinates for infinitesimal intervals and the abscissa, so the sum of infinite rectangles. From these definitions, he quickly identified the relationship of integration with differentiation, and he realised the potential to form a whole new system of mathematics. In 1684, he published his work on the theory of calculus, which included differential and integral calculus completely independently of Isaac Newton. As Newton hadn't published anything on calculus yet, a controversy arose as to who discovered calculus first. Eventually, Newton was credited as the first discoverer, and Leibniz was credited with the first to publish work. Over the years, they have been both accepted as independent discoverers of calculus. It was Leibniz who thoughtfully used superior notation to Newton, which is the notation used today in modern calculus. If we compare the calculus of Newton and Leibniz, the descriptive terms to describe change by both mathematicians was essentially very different. For Leibniz, change was the difference ranging over a sequence of infinitely close values called infinitesimals. These are the basic ingredient in the infinitesimal calculus developed by Leibniz. Infinitesimals for Leibniz were the small quantities such as the tiny rectangles and the tiny gradient values of the secant eventually approaching 0. They are so small, in fact, that there isn't any way of measuring them. Later on, mathematicians would describe this as a limit. The rise of calculus by Newton and Leibniz in the 17th century was such a unique and significant moment in mathematics. It was a whole new system and form of maths to help describe our dynamic universe. The benefits of using calculus to model any system of change or motion today is virtually unlimited in any field, such as medicine and economics, and is not restricted to physics only. We can appreciate Newton and Leibniz for pushing civilization forward in such a dramatic way in the 17th century by connecting the physical universe of motion and change with mathematics.